Hi, my dear brothers and sisters. Have a great day to everyone. Previous class, we discussed about the numbers and Euclid's division algorithm of chapter 1 real numbers. Today we are going to learn HCF, highest common factor, and today we are going to solve problems of exercise 1.1 of first chapter real numbers. Okay, now let's begin with HCF, highest common factor. Real numbers. Real numbers. Find the HCF, highest common factor. Highest common factor of 60 and 100 using Euclid's division method. Find the HCF of 60 and 100 using Euclid's division method. Okay, when 100 is divided by 60, the remainder is 40. Look here, 100 is divided by 60. Okay, 60 divisor, 100 is dividend, 60 ones 60 minus 0 borrowing 10 minus 6 4. 100 is divided by 60, the remainder is 40. Okay, look here, we remember the formula of Euclid's division method. A equal BQ plus R, 0 less than or equal to R less than B. Look here, B is 60, Q is 1, R is remainder is 40. Okay, 100 is equal to A. 100 is A. A is equal to BQ, 60 into 1. This is divisor, this is quotient, plus remainder 40. Now consider the division of 60 with remainder 40. In the above equation and apply apply division algorithm. Now consider the division of 60, with the remainder 40. Okay, division of 60 with the remainder 40. 40 ones 40, 0 minus 0, 6 minus 2, 6 minus 4, 2, 20. Dividend 60, divisor 40, quotient 1, remainder 20. Now 60 is 40 into 1, 40 into 1 plus 20 plus 20. Now consider the division of 40 with remainder 20 and apply division algorithm. Okay, now division of 40, this divisor changes into dividend, this remainder is changes into divisor. 22 is a 40, 0, 0. The remainder is 0. Now the problem is end. Okay, 40 equal 20 into 2, 20 into 2 plus remainder 0. Okay, now the HCF of 60 and 100 is 20. Now we get HCF 20. This is the last divisor, goes into highest common factor. 20 is the highest common factor. Now we can easily verified by writing all the factors of 60 and 100. Okay, now we can easily verify it by writing all the factors of 60 and 100. Factors of 60 called, one is factor of every number, 1, 2. 60 is divisible by 2. 60 is divisible by 3. 4 also factor, 5 also factor, 6 also factor, 7. 60 is not divisible by 7. 60 is not divisible by 8. 60 is not divisible by 9. 10 is also a factor. Next to 11, 12. 12 also a factor. 12, 13, 14, 15. 15 also a factor. 16, 17, 18, 19, 20. 20 also a factor. 22, 25. Next to 30. 30 also factor, and 60 also factor. Look here, 1 is factor of all the numbers, and given number is also factor of that number. 60 is own factor, 1 is factor of every number. Next, factors of 100. Factors of 100. 1, 2, 3 is not factor of 100. 4 is factor of 100. Next to 5 also factor of 100. 6 not factor of 100. 7, 8, 9, 10. Next 11, 12, 13, 14, 15, 16, 17. Next 20 is a factor. Next 25 also factor of 100. Next 50, then 100. These are the factors of 100. These are the factors of 60. Okay, now look here. Now check what is the common factor. What is the highest common factor of 60 and 100? Check, 1 is common factor, 2 is also, 4 is also, 5 is also, 10 is also common factor, 20 is also common factor, but 30 not in the list, 60 also not in the list. So highest common factor is 20. 20 is common factor, highest common factor of 60 and 100. The HCF of 60 and 100 is 20. Now verified by the all factors of 60 and 100. Okay. Now we are going to our 10th class maths textbook, page number 8. Here is some problems. Do this. Find the HCF of the following by using Euclid algorithm. Okay. Here first one is 50 and 70. Second one is 96 and 72. Third one is 300 and 550. Fourth one is 1860 and 2050. Okay, now go with fourth one, 1860 and 2050. 1860 and 2050. Okay, 2050, 1860, 1861's 1860, 5 borrowing from 2, 11 minus 6, 5, here is 9, 9 minus 8, 1, here is 1 minus 1, 0. Okay, now write 2015 is equal to 1860 into 1 plus 155. Okay, formula A equal to BQ plus R, 0 less than or equal to R less than B. Okay, now 155 is the divisor. Next 1860 is the dividend. Okay, 155 once, 155 minus 6 minus 5, 1, 8 minus 5, 3, 1 minus 1, 0. Then 0 comes 155, 310. So 155 2s are 310. So 0, 0, 0, 0. The remainder is 0. Next to 1860. 1860 equal to 155 into 12 plus 0. Okay, remainder is 0. The problem is completed. The HCF of 1860 and 2015 is 155. 155. This is the highest common factor of 1860 and 2015. Look here, 155. This is the last divisor. So this changes into the HCF of 1860 and 2015. Okay. Now we are going to exercise 1.1, page number 12. First bit is use Euclid's algorithm to find the HCF of first one is 900 and 270. Second one is 196 and 38,000. One is 1651 and 2032. Okay, now we are going to third one, 1651 and 2032. Okay. Use Euclid's algorithm to find the HCF of 1651 and 2032. 2032, this is dividend. 1651, this is divisor. Okay, 1651 once, 1651 minus 2 minus 1 1 borrowing 13 minus 5 8 ఇక్కడ 9 minus 6 3 okay 0 2032 equal 1651 into 1 plus remainder is 381 okay then ikkada 381 is changed like divisor 1651 is changed into dividend okay 381 1651 so 4 nearly 4 times 4 ones are 4 4 8s are 32 2 3 carrying 4 3s are 12 12 plus 3 50 okay here 1651 4 times 15 24 borrowing 11 minus 4 7 4 here is 4 4 minus 2 2 next 6 minus 5 1 1 minus 1 0 127 okay 1651 equal 381 into 4 plus 127 this is remainder okay now 127 381 127 remainder is change into divisor divisor change into dividend 381 127 nearly 3 times okay check once 3 7s are 21 1 2 carry 3 2s are 6 6 plus 2 8 3 1s are 3 okay 381 3 times 381 minus 1 minus 1 0 8 minus 8 0 3 minus 3 0 the remainder is 0 the problem is completed okay 381 is equal 127 into 3 plus remainder is 0 so the HCF of 1651 and 2032 is 127 last divisor is 127 so 127 is the HCF of 1651 and 2032 the HCF of 1651 and 2032 is 127 okay now we are going to second problem second question from the exercise 1.1 use division algorithm to show that any positive odd integer is of the form 6q plus 1 6q plus 3 or 6q plus 5 where q is some integer okay now we are going to solve the problem solution here a can be a positive odd integer and b equal here look here our Euclid's division formula a equal bq plus r A equal BQ plus R. Here B is 6, 6Q plus 1, 6Q plus 3. So B is 6. We apply the division algorithm A and B equal 6. Okay, A can be A equal 6Q plus R, Q greater than or equal to 0 and 0 less than or equal to R less than 6. Here B is 6. So the possible reminders are 0, 1, 2, 3 or 4 or 5. Look here, A equal BQ plus R, B equal 6. Remember, always remainder is less than B. Remainder is less than divisor. Here divisor is B. B equal 6. So the reminders, the possible reminders are 0, 1, 2, 3, 4 or 5. These are less than 6. Less than 6. 6 is greater than these numbers. So these are less than 6. So A equal 6Q or 6Q plus 1 or 6Q plus 2 or 6Q plus 3 or 6Q plus 4 or 6Q plus 5. The possible remainders are 0, 1, 2, 3, 4 or 5. So we get A equal 6Q or 6Q plus 1 or 6Q plus 2 or 6Q plus 3, 6Q plus 4 or 6Q plus 5. Look here, 6Q plus R. These remainders are 0, 1, 2, 3, 4, 5. So 6Q if remainder is 0. If remainder is 1, 6Q plus 1. If remainder is 2, 6Q plus 2. If remainder is 3, 6Q plus 3. If remainder is 4, 6Q plus 4. If remainder is 5, 6Q plus 5. Look here, 6Q. This write like this, 2 of 3Q. Here 2 is common. 6Q plus 2. This write like this, 2 of 3Q plus 1. Here 2 is common. Next 6Q plus 4 equal 2 of 3Q plus 2. These numbers are divisible by 2. Look here, 2 into 3q, 2 into 3q plus 1, 2 into 3q plus 2. So these all numbers are, these three numbers are divisible by 2. So the numbers cannot be odd positive integers. Look here, these are even numbers. So our question is the form of 6q plus 1, 6q plus 3 or 6q plus 5. Any positive odd integer. These are even numbers, so these cannot be odd positive integers. So therefore any positive integer, odd integer a can be the form of 6q plus 1, 6q plus 3 or 6q plus 5. Okay. This is completed. This is solved. Okay. Third question of the exercise 1.1. Use division algorithm to show that the square of any positive integer is of the form 3p or 3p plus 1. Okay. Now solve the problem. Solution. Let a be any positive integer and b equal 3. A equal to bq plus r. This is our Euclid's formula. Here b is 3p or 3p plus 1. So b is 3. We can apply the division algorithm a and b equal 3. We get the possible a can be a equal 3q plus r q greater than or equal to 0 and 0 less than or equal to r less than 3. So the possible the possible reminders are here b equal 3. So the possible reminders are 0 or 1 or 2. Reminders are less than divisor b. So the reminders are 0, 1 or 2. Now a equal 3q when remainder is 0, or a equal to 3q plus 1 when remainder is 1, or a equal to 3q plus 2 when remainder is 2. So now let's take the square of these numbers. Let's take the square of these numbers. Here look, our question is to show that the square of any positive integer is of the form 3p or 3p plus 1. Let a be any positive integer. Now we go the square of these numbers. First case, a equal 3q, a square equal 3q whole square 9q square. This like this 3 into 3q square, 3 into 3q square. Here it is of the form a square equal 3p, a square equal 3p. Here p equal 3q square. Okay, here it is of the form of a square equal 3p. Look, this is like a 3p. So here p is 3q square. Now second case, a equal 3q plus 1, 3q plus 1. A square equal 3q plus 1 whole square equal a plus b whole square. This is like a plus b whole square. So 9q square plus 2ab, 2 into 3q into 1, 6q. 6q plus 1 square equal 1. This like we get 3 common from this numbers, 3 into 3q square plus 2q plus 1. It is of the form a square equal 3p plus 1. 3p plus 1. So here p equal 3q square plus 2q. Look here, this is like 3p plus 1. So here p equal to 3q square plus 2q. Now going to third case. A is equal to 3q plus 2 plus 2. A square equal 3q plus 2 whole square equal, this is like a plus b whole square. A square 9q square plus 2ab. So 2 into 3q into 2. 2 into 3q 6q, 6q into 2 12q plus 12q plus 2 square equal 4. So this is right like this. 3 common, 3q square plus 4q plus 1 plus 1. 4 right like this plus 3 plus 1. So we get 3q square plus 4q plus 1 plus 1. It is of the form a square equal 3p plus 1. Here p equal 3q square plus 4q plus 1. So our first case, this is like a square equal 3p. Second case, this is like to a square equal 3p plus 1. Third case, a square equal 3p plus 1. So our problem is solved. Use division algorithm to show that the square of any positive integer a and a square equal 3p or a square equal 3p plus 1. This is like this form, 3p or 3p plus 1. Okay, our problem is completed. Okay, look here, fourth and fifth question also given in the exercise 1.1. These problems also can solve as this method. Okay, our exercise 1.1 is completed.